Okay, so we're going to do nitration. So the first step, we have, a lot of times you'll see it look like this. HNO3, H2SO4. So the first thing we need to do is activate the electrophile, form a strong electrophile. And to do that, we take our nitric acid, which has this Lewis structure, and it's going to react with our sulfuric acid, which of course has this Lewis dot structure. Right? So they're both strong acids, but at the end of the day, somebody has to be the base. So in this case, the weaker acid is going to be the base. Right? So the nitric acid is weaker, so it's going to act more like a base. So the oxygen is going to be the nucleophile. The H on sulfuric acid is the electrophile. What that's going to do then, generate for us so now we have nitric acid that has been protonated, right? We have the water, basically like a water molecule here. And so if you look at this bond between oxygen and nitrogen, right, they both have plus charges. Oxygen is more electronegative than nitrogen. So it makes sense that this bond would be weak. So what's going to happen then is these electrons here come down, and in doing so, they break this bond. And so what you generate then, you have lost water, right? You've also made nitrogen that is now double bonded to two oxygens. You make that new pi bond right here, this bond breaks, and you get this nitronium ion, which is a really, really good electrophile. Okay? Let me keep going with the next step. Right, so now that we have a really good electrophile, let's just kind of wall this off a little bit. We take our benzene ring, and we're going to have it react with that, right? Benzene is not a very good nucleophile because it's very stable, so we have to have a really strong reactive electrophile. So the pi bond of the benzene ring attacks, electrons kick up, and we form our first intermediate, our first sigma complex, we could call them. One oxygen has a negative charge, the nitrogen has a plus charge. Another plus charge here, because we want to make sure we balance our charge overall, right? Has to be up here in our first part, it was overall plus, so we got to make sure it's overall plus here in our last step. There's our nitronium. A good electrophile. All right, we'll do sulfonation. Whoops. So sulfonation, we're taking an aromatic ring, and we're going to react it with two H2SO4s. That's going to give us a sulfonated aromatic ring. All right. So this is similar to the nitration one, or where we essentially have to activate the nitro group. Here we have to do an activation to get the sulfonation to happen. So if we draw the Lewis dot structures of both sulfuric acids, or two sulfuric acids, just like with nitration, somebody has to be the base. All right. So it doesn't matter which sulfuric acid is the base. So this time I'm going to take this one. Takes the hydrogen, right? right? Similar situation we had before, right? We have a water molecule kind of sitting here. So we have oxygen with a plus charge, bonded to sulfur, right? This sulfur is pretty delta plus because it's bonded to these other oxygens. So this bond is pretty weak. So what can happen is the lone pairs from this oxygen can come down, and they'll break the oxygen sulfur bond. And what you'll end up with, of course, is water, which is a pretty good stable molecule. And then a sulfononium ion, right? That again looks like a pretty good electrophile, right? If you think about this sulfur atom, that's pretty delta plus. It's got all these oxygens pulling on it. That's a pretty reactive molecule. So the next thing, I'll just show you how it happens really quick. Pi bond attacks, breaks this oxygen pi bond, and now you have your intermediate sigma complexes started. Plus charge there, S. And anytime, of course, after we do a mechanism step, we gotta make sure our charge is balanced. Our charge is overall plus. There's overall plus 1 in the start material, so we're good there.